Hey Calc, we're going to have a really big show tonight. We have the second month, the 8th day, the 17th year. So we're looking at this after Wednesday's class. So let's see what's on our plate. Would you write down this definition, please? It says, seems to be a glare here. I don't know why, more than normal. A function, capital F, is an antiderivative of little f on an interval I if the derivative of capital F equals little f. So write that down. You can pause it for a second or two while you write that down. I'm going to go on. All that's really saying is this. So I think it's a little more clear with symbols. It means if you take the integral of a function, f of x dx, you will get capital F of x. We always call the integral we denote the integral with a capital F, and the function, which is going to be taken the integral of, is going to be smaller f, and as we discussed previously, plus c. All of these parts have a name, so I'll just go ahead and wade through them. Alright, so this part is called the integrand, the one behind the integral sign. The dx or dy or dt, whatever, tells you the variable of integration. This with the capital F indicates an antiderivative. And the C is called the constant of integration. So again, pause the video to get those down. And then as we go on, I just want to make a note here that when I say, or someone says antiderivative, it's exactly the same as saying the indefinite integral. So we haven't learned the difference between an indefinite and definite integral. So as far as you're concerned, an antiderivative is the same as an integral. All right, so another way, putting all this together, and I mentioned yesterday that an integral and a derivative are opposites, like multiplication and division. So here I put that in symbolism, and I say the derivative of an integral is f of x. So I'm taking the integral of f of x and then taking the derivative. It undoes what the integral did, and it gets us back to the original function. So one undoes the other. So we're going to add to our list of integrals, and we can obtain integration formulas from differentiation formulas because the derivative and the integral are so related. One undoes the other. So let's start then with the derivative of a constant we learned was 0. Or is 0. So I can say the integral of 0 dx. This is where it is important because you have no clue what the variable in the problem is unless I put the dx here. So that will just be the integral of dx. 0 dx is just the constant c. See how I started with the c, took the derivative, and got 0. So I can go backwards with the integral by integrating 0, which I will never really write the 0. It'll look like this. The integral of dx is just a constant c. Alright, so let's keep going on that line of thinking. The derivative of some constant times x, such as 3x or 1/2 x or whatever, is always that constant. So going backwards, I'm going to take the integral of k dx, and that is going to get me just back to where I was over here. It's going to be kx plus c. All right. Moving right along. All right, this one isn't exactly backwards, but it'll get us some information. The derivative of the sum of two functions is the sum of their derivatives. So we can think similarly, and I actually mentioned this previously, so you could do a couple extra problems in class. I don't think we got to them, but I mentioned that it works similarly with the integral. So the integral of a sum, so say we put the sum behind the integral, and we're going to get, we can divide that up into two individual integrals. So the integral of a sum is the sum of the integrals. All right. Let's go on with the derivative of a constant times a function this time. So what I want to demonstrate for you here is if we had a function in x but a constant in front of that, then that k will appear in the answer in front of the derivative of the expression x. So, in a sense, the k crossed over the derivative sign and was unaffected by it, the constant. So, let's see how that works with integration. And I mentioned this also yesterday, but to get it down once more, we can say that the integral of k, f of x, dx, is always going to be k can cross the integral sign and we get the integral of f of x dx. So any constant can cross the integral sign but no variable. Alright, the big deal yesterday was related to this statement, and we say the derivative of x to the n runs down in front, and then it becomes n minus 1. So it's not very, I could take the integral of this and get back to this, but this doesn't pop up so often. What does pop up is the integral of x to the n dx. And I want to know what that is. It's closely related to this. So notice the relationship, and we'll try to develop the relationship here as well. So notice when we go backwards, this expression, the integral, the exponent of the variable went from negative n minus 1 to n. It increased by 1. So that's what's going to happen over here. So we're going to get x to the n plus 1. And then to make it work out evenly, and I'm going to show that it does, I have to also divide by that new exponent. So this is going to be true if I take the derivative of this expression, and I can get back to here. So what is the derivative of x to the n plus 1 divided by n plus 1 plus c? What is the derivative of that with respect to x? Well, the derivative is, this is just a constant, so it's going to appear unaltered in the answer. This is the variable. It's going, the n plus 1 is going to run down in front, and it will reduce by 1. So n plus 1 minus 1 is n, and the derivative of a constant is 0. The n plus 1's cancel, and we get x to the n, which is what I was hoping if this was the correct answer. It is. So you can see then a little bit more about why that is. We were using it today. All right. Let's go on and just add a couple more and call it a night. The derivative of sine is cosine, so I can reverse that thinking with my integral. The integral of cosine is going to be sine. Let me zoom in a little bit. looking kind of small. All right, so then the derivative of cosine is minus sine. So I don't often find the integral of negative sine. I find it more helpful to find just the integral of sine. But this relationship will help me. So if the integral of negative sine is cosine, what do you think the integral of positive sine is? It's going to be negative cosine. All right, so we have to keep this straight. The derivative of sine is cosine. The derivative of cosine is negative sine. But the integral of cosine is sine, and the integral of sine is negative cosine. So, good luck with that. The derivative of tangent is secant squared. Doesn't come up a whole lot, but when it does, we know that the derivative of secant squared is tangent. All right. The next one, the derivative of secant x is secant tan, and the integral of secant tan is secant plus c. All right, and there's just two more of those kind. Derivative of the cotangent is negative cosecant squared. Again, I'm going to just find the integral of cosecant squared instead of the negative, but looking at the relationship, you can probably foresee that the answer is going to be negative cotangent x plus c. And the last one that we should already know these, the derivatives. So derivative of cotangent is negative cosecant squared, and then we go to the derivative of cosecant x is negative cosecant cotangent. So I'm going to do the integral of the positive, which will, dx will give me this answer except with a negative. All right. That's all the preparation to get you ready for your work tomorrow. So glance over it, chew it up, digest it, and bring it with you. I'll see you tomorrow. Bye-bye.